We're live.
Awesome. Welcome, everyone. My name is Sanskriti Deva. I'm a product marketing manager here at IBM Quantum, and this is super full circle for me because one of my first touches with Quantum was actually Qiskit Global Summer School. And I'm here with the amazing Chris Porter, who is a quantum content and communications manager, as well as a physicist. And I think we might have briefly lost Chris, but today we'll get the opportunity to ask Chris any questions that you might have. So feel free to drop them into the Q&A. And while we wait for Chris to get back on, um, oh, there he is. Hey, Chris, can you hear me? Hello? Cool. Some technical difficulties, I think. Hello, can you hear me? Yeah, not again, technology. Okay, yes, sign out and sign back in. Cool. But while we wait for Chris, we hope you've been enjoying Kiskit Global Summer School. Like I said, it's super full circle for me to be on this side of things, and it's a great opportunity to dive into the world of quantum. While we wait, feel free to, in the chat, put a lecture that you're looking forward to, or a lecture that you've enjoyed, or a lab that you've enjoyed so far. Someone said they really liked John Preskill's session. Yep, that was one I was looking forward to as well.
Hey,
Hey, Chris, can you hear me?
yes, can you
Yay!
hear me?
Yes, perfectly. I feel like classical computers are sometimes harder to solve than quantum computers, in my experience. But so great to have you, Chris. Again, Chris is a quantum communications and content manager as well as a physicist. So we're so excited to be able to have Q&A with him today.
Thanks so much. Yeah,
Awesome.
yeah. Sorry about the snafu there. I'm not sure why I got kicked out, but hopefully everything runs smoothly now. And like you, I can't wait until quantum computers replace classical computers. That's not a real thing. I'm just teasing.
Yep. Quantum futures or quantum present. So with that, let's dive into our question. Um, so the first question is, could you recommend a good project on quantum information and algorithms for undergrads preparing for internships, or could you provide any in-depth resources where they could get started with such a project?
Yeah. So the in-depth resources, let me go backwards. I'll answer the latter part first. The in-depth resources, I would say that our IBM Quantum Learning Platform is a really great place to learn about algorithms, learn about different approaches, and also some of the contexts in which they can be applied. So, for example, if you were looking for a new algorithm, one of the more promising ones to apply to like a research question, there's a course called Quantum Diagonalization Algorithms, which focuses on sample-based quantum diagonalization and shows a little bit about sample-based quantum Krylov diagonalization. These are really, really promising approaches, and it shows how to apply them to like chemistry problems or like a physics problem, like spins on a lattice. And so that's a great resource to frame not only like what are the promising approaches, but also where could you use them. Um, Beyond that, more generally, I would say that right now sample-based algorithms seem to be the most promising ones. And so if you can find an application for that. That would be the best. There is always the quantum error mitigation and error correction route. So looking into what you can do with that, it's less. It's like one step removed from an application to industry in the sense that if you want to solve like the structure of a molecule or something like that, then you really want to learn how to do something like SQD and actually like solve the industry's problem as opposed to that one level higher where you're trying to make quantum computing better through error mitigation and error correction.
No, that's a great call out, especially mentioning that you can work across the stack, so don't just limit yourself to applications, as well as our learning platform, which is also another way that I got started with my quantum research journey. There's like a lot of great tutorials there. The next question is about quantum algorithms. How can quantum algorithms that we talked about be applied in research? For example, is there any use case of Grover's algorithm being applied in physics data searches or something like that?
Oh, interesting. I think you went right to the one, the questioner went right to the one that I would have called out as having applications in the sense of being like a subroutine in other quantum algorithms. So, for example, if you're looking at Deutsch's algorithm, it's hyper specific, looking for something that's balanced or constant. If you look at Shor's algorithm, I mean, in that it's got machinery that leverages quantum phase estimation. It's general in that sense. It's got some general structures to it, but the overall point of the algorithm is to factor large numbers, and it's again very like hyper specific. The two in the middle, chronologically in the lectures, Grover's algorithm and quantum phase estimation, those are the ones that I think are most likely to have very general applicability in other algorithms and in approaches to solving problems for industry. So for Grover's, simply looking for something looking for a function that satisfies your criteria in a quantum algorithm where you might be working with a lot of quantum data, so data that have already been loaded onto your quantum computer. One can imagine how that could be widely applicable. In fact, it's so applicable that I struggle to say exactly where, because it's like anytime you're looking for something. Quantum phase estimation, I can give a bit more of a concrete answer. So quantum phase estimation is all about estimating what that phase is that's out in front of your state. And if you're familiar with quantum mechanics, and I know John talked about it a little bit, but the time evolution operator in quantum mechanics is an exponential of the energy of a state. And so, I mean, it's the propagator for those who've taken quantum mechanics. And so if you could estimate the phase out in front of that state for a given amount of time that's elapsed, you would be estimating the energy effectively, up to an H bar or whatever. So that would have tremendous applications in just like finding the binding energies, finding ground state energies, that kind of thing. So that would also have very broad applications, potentially within other algorithms, but also just very direct in terms of what is the ground state energy of this system? What is the ground state energy of a chemical, that kind of thing.
Wow, that's so cool. And then the next set of questions, I'm going to group them together, are along the lines of I'm an undergraduate student, or I'm someone who studied math or CS, or I come from this specific background. How can I dive into the world of quantum computing, and what would you recommend to me if I want to start a career in this field?
Yeah, so I can say a couple of things about that. The first thing I'll say is a shameless plug for our learning platform. Again, you should go check it out. It's got great stuff. It's got John's stuff actually. So I saw in the discussion people were talking about how some of the content that was presented has already been canonized over on the quantum learning platform. And there's a lot more there. So John has a course that's the basics of quantum information that comes before all of this algorithm stuff. He has a course that is chronologically after this content, that's generalizations of quantum information. And he's got one on quantum error correction. So this is a really nice sequence, a really nice arc to go through. And if anybody was watching John's lectures, struggling to keep up because he's fast, it's a great opportunity to go through it at your own pace and to also do a little bit of scaffolding before some of what he was talking about by going back to that first course, the basics of quantum information. One nice thing about that is that at least currently the first two courses are badged via Credly. So you can go onto the learning platform, take the course, and then follow a link out to an exam and get a Credly badge. And those are nice stepping stones toward like higher credentialing, like maybe the Qiskit developer certification. That's something that really stands out. So when people have a Qiskit developer certification, it really signals that, you didn't just take a course, you took like a suite of courses and maintained interest over a long period of time. So that's a great way to sort of um, distinguish yourself. If you want to go beyond that, if you want to go beyond just taking some going through some coursework and taking an exam, I'll tell you one interaction that I've had that was especially impressive to me being in industry is I've talked a little bit with students from universities who have started their own like quantum computing club. Like they'll just take it upon themselves to organize, ask the department for some money, something like that, and you get pizza and donuts, get together, talk about quantum algorithms. One group in particular that I've been talking with actually made their own suite of like YouTube lectures, and so that, I mean, if you could say you did something like that, that shows tremendous initiative and investment on top of the badging and the credentialing. So, and of course, just the community of learning and the community of practice is tremendously valuable as well.
Yeah, no, I second all of that as someone who recently made the transition from student to industry. And we also have a panel that will be a part of QGSS talking more about careers, and we'll give next steps towards the end of QGSS. So really exciting stuff, and very well put. The next question I really like because it's asking, in Grover's algorithm, the geometric interpretation, it often offers like an elegant visual understanding of quantum amplitude amplification. Do you think there are other classes of quantum problems that could benefit from geometric or visual interpretations? I know we have amazing design teams that already work on this and do a lot of work with this, but I would love to know your take on this, Chris.
That's interesting. There are a couple of ways of answering that. The first is like mapping other algorithms as like one to one as you can to Grover's algorithm. There's a distinction to be made, and that is that there are approaches that involve measurement and then like post analysis, and then there are other algorithms that you just do the measurement at the very end, and that gives you the state that you're looking for. So anytime that you are performing only unitary operations, which all of our quantum gates are, anytime you're only performing unitary operations, there could be a geometric representation. That what space that geometric representation lives in gets tougher and tougher, and like if you're in very high dimensions, or gets more and more interesting, I could say. But there should be some kind of geometric interpretation because you can cast all of these unitary gates as rotations in a Hilbert space. Now, algorithms that use measurement and then do like post hoc error correction, or use the measurement to obtain samples of a ground state, or samples of a space that hopefully contains your ground space state. So like sample-based diagonalization algorithms, those leverage measurement very heavily and do a lot of the calculation after the fact. And so those would have a less obvious connection to the types of reflections and rotations that John was outlining for the Grover's algorithm. They do have like they can be visualized though. There's actually a really great visualization done by as you were saying, somebody on our design team. It's in the quantum diagonalization algorithms course on learning. We should drop a link somewhere. It's in the third lesson. There's a video that shows how the sampling approach works, where you've got like an astronomically large matrix, and then you do some quantum mechanical sampling to see what states are sort of relevant for finding your ground state, and then you project your Hamiltonian matrix onto that subspace, and it like reduces the dimensions of it, and you can see this like a visual representation of the matrix being shrunken down by only taking the columns and the rows that are most relevant to your problem. I think that's already very helpful, picturing like what you're doing when you say, you know, project onto a subspace. It means take the rows and the columns that are important. So I think there's always a way of visualizing what's going on. It won't always have such a one-to-one mapping with rotations in a Hilbert space or reflections the way it did in the Deutsch algorithm.
I like that. And I love how you knew exactly where that image was. That's very impressive. I don't think I could have remembered that.
Well, it's that impressive. It's that he did that good of a job. I think that's right though. I think it's the third lesson.
Nice. So for our next question, one of our attendees would love to know your thoughts on post-quantum cryptography. They're asking when will it become real and what will be its impact?
Post quantum cryptography. So that's basically my opinion is that it's really important. So depending on what somebody's background, and we could say a lot or a little bit about this. One thing, if you're really interested in um, quantum computing and you're interested in quantum algorithms and that kind of thing, there's a sense in which you don't really have to worry about that so much right now, because the issue is that quantum computing will be able to break RSA and many other types of cryptography. And so, what really has to be done from the post quantum cryptography perspective isn't make new quantum algorithms, but rather make new types of security algorithms that are not quite so at risk from quantum computing. And so, if your interest is primarily in new quantum algorithms, then that only kind of tangentially touches on what the cryptography will be after quantum computing breaks some of the types of encryption. So you should care about it, but the sort of paths of research are only they're only tangentially related. So there are immediate concerns about quantum safe cryptography, in the sense that there's this mode of operation that nefarious actors might pursue called harvest now, decrypt later. I think that's the terminology that's used, and it means gather encrypted data now when everything is secured using RSA 2048 or whatever the server might be using, and decrypt it as soon as a quantum computer can run Shor's algorithm on a number of that size. And so from that perspective, they're harvesting it right now. And so you don't have to wait for the quantum computer to be relevant in order to start caring about the security of your data. So from that perspective, it's relevant right now. From the perspective of when we're actually able to break that, I wouldn't want to hazard a guess about exactly when we're able to break that, except to say that we are already able to do calculations that sort of give classical computers a run for their money. We've been playing this interesting game in the utility era where quantum computers will do something that classical computers couldn't do or hadn't done yet, or that kind of thing. And then classical computers will figure out a way, a cleverer approach, and they'll be able to do the same thing. And we'll sort of play this game of one-upsmanship. So we're already in that era where we can kind of push classical computers. There have been estimates about reaching quantum advantage within the next 2 years. And so it's it's a time scale that we should care about. It's a time scale that's like on the order of an undergraduate degree, that we have to care about these things. And like I said, depending on the threat of harvest now, decrypt later, it could be of utmost importance right now.
No, I really like that. And I love that you emphasize that a lot of work is happening in the field right now. especially since we have the quantum safe business unit at IBM that's working on it. So
Yeah.
super cool stuff happening like all across these applications. Um, and that leads into my next question. What do you think are some areas in quantum that people often overlook but have a lot of potential?
Places that people overlook in quantum computing but have a lot of potential. I mean, presumably, I would be one of the people overlooking it.
Right.
Overlooked. We might have to let that one stew for a minute. I mean, I can say that there have been a number of there have been a number of algorithms and approaches that have risen to the forefront of everyone's mind, where everybody thinks like, well, that's where we're going to see quantum advantage, and then it sort of falls to the wayside as something new comes up and is enthralling. So there are lots of areas that some people might have sort of dismissed that I don't think we're done with yet. Um, but I, I'm not aware of anything that people are just totally glossing over. Um, like I'll give an example. I think that I, maybe I shouldn't give an example. I think that there's still a very active role for like variational Ansätze, for example, to play a role in like sampling based techniques. I think that a lot of the tools that have been developed over the last decade or so are going to be leveraged together in one algorithm, and I think that you're seeing that already a little bit in sample-based quantum diagonalization and SKQD. That's sort of the quintessential example where different approaches, Krylov quantum diagonalization and sample-based diagonalization, came together to give us something that's really, really powerful. And so when you hear that something doesn't scale well, take that seriously. If you hear it doesn't scale well, it doesn't scale well. But don't discount that entirely as a tool. It's still a tool in our toolbox that might be leveraged in as part of a larger algorithm. I'll say
Yeah,
that.
no, I really Yeah, I actually really love that answer because you mentioned that the technology is really a tool for the community and the ecosystem to use and figure out what problems we can apply to in many cases. And so I guess we'll pass that question back on to you guys and say, show us what you can do with it.
Yeah, please tell us if there are areas that you think we're overlooking. Yeah.
Exactly. But great question. So our next question is, do you need a PhD to be in the quantum computing industry? And I don't have a PhD and I'm in the industry to preface. So it's definitely possible, and I know a lot of people who don't have PhDs, but would love to pass that on to you, Chris.
Yeah, that's a great question, and it's something we hear a lot. And I think that to some extent the answer is we don't know yet because we don't know what the jobs will be that emerge. Um, I will say that I've benefited greatly from having a PhD. A lot of what I did in my PhD and in my postdoc really paid dividends in my current role. So I recommend a PhD, but uh, it is definitely not a sure thing that you will need a PhD in, say, for example, physics or computer science or math for perpetuity. So there's going to be uh, a lot of opportunities for people who are subject matter experts in the fields that will benefit from quantum computing. So, being highly educated, whether it's a PhD or not, but being highly educated and experienced in something like chemistry or biochemistry, I think could potentially have applications or could have a quantum related jobs in the future. One place to so there are jobs pages, there are quantum jobs pages where you can go and look at what people are looking for. And there's certainly a lot of people who are being sought who have PhDs and many years of experience. That's definitely, I don't want to downplay the importance of a PhD. But what you find is that there are a lot of jobs listings for people who have master's degrees and some experience, or even a bachelor's degree. If we expect quantum computing to behave anything like classical computing. So in the early days of classical computing, everything was a research project and everybody had a PhD and everybody was at a university. And then, by the I'll get it wrong if I specify a decade. I want to say by the 80s, like most of the practitioners just had bachelor's degrees. I'm not sure if that's true. You should check the year, but there was a big democratization in the sense of moving away from PhD and master's level only toward anybody who had like an undergraduate education in computer science. And one could imagine that quantum computing could follow suit. But certainly right now, PhDs are paying dividends.
Agreed. And I love how you touched on your personal journey there, because the next question is about how your personal experiences with a background in physics and now as someone who puts out content and educational material into the world, has shaped you, and what's the biggest lesson that you've learned from your personal journey?
That's a really nice question. Like, thanks. Gives me a chance to talk about myself. That's a good question. So I took a very strange path. Uh, I I did a PhD in condensed matter theory, and then I was briefly faculty, and I actually went back and did a postdoc in physics education research because I was absolutely fascinated with the way that people engage with this really challenging content, especially quantum mechanics. And I did a lot of research on student understanding of quantum mechanics in particular. And so that really, teed me up perfectly for this role. So I have a PhD in condensed matter theory, so I understand a lot of the inner workings of the quantum computers, um, but it's certainly not all. But I also did spend a lot of time thinking about how people engage with this. What are the resources that people can bring to bear on quantum computing? And also, what are the misconceptions? What are the misconceptions that just persist all the way through a PhD and beyond that people just never get free of? And how can we combat those up front? And so that was the perfect background to be working in quantum computing and developing content. Um, but there was something else. Did they say what's the most important thing that we've learned? Is it something like
Yes, what's the most important lesson you've learned?
that? I would say don't underestimate the importance of the zone of proximal development. So in education theory, there's the famous book by Vygotsky where they sort of outlined this thing called the zone of proximal development, which is like you have some resources that you can bring to bear on a problem, and you have sort of some cognitive environment, things that you're comfortable with. And if you stay, in the proximity of that, where you can leverage things and you can sort of see you have scaffolding around what you're trying to do, then you can grow. If you're just dropped into something that is totally outside of your comfort zone, you'll really quickly reach cognitive overload and struggle a lot. And when I would say just acknowledge that that's what's happening. Like it happens to me all the time when I'm doing quantum computing that somebody will start talking about maybe John, and I'll think like, oh man, I need to, I don't know what he's talking about. I got to go back and review this. It's okay. It's absolutely okay. It's not that you don't have the background for this, you're not the kind of person who can do this or anything like that. It's that you are outside the zone of proximal development. Go back to your zone of proximal development and extend the boundary with the unknown a little bit, and then you'll get there.
I really love that. I feel like in quantum you have to be comfortable with being uncomfortable just because of the like rapid advancements in the field. And so I think that's a great takeaway for people who are joining QGSS to have, because I'm sure there's going to be a point in their quantum journey where they'll feel uncomfortable. So thank you for that. I'll definitely take that with me. So we have about 30 seconds left. And so the last question I would love to ask you, Chris, is what is something that you're looking forward to in QGSS or in general in the quantum industry?
I'm really excited about the combination of sampling-based methods and the Krylov method, which I've mentioned a couple of times, this SKQD, sampling-based quantum Krylov diagonalization. I'm not sure if I said those words in the right order, but that one, I'm really excited about that because it's efficient. It comes with convergence guarantees under the right conditions. I'm also really excited about the combination of error mitigation and error correction because I think we're going to be able to tackle deeper and deeper circuits and start to see um, some of these canonical algorithms come into play as well.
Awesome. Well, thank you so much, Chris, for being with us here today. And I know we weren't able to get to all of the questions, so feel free to pop those questions into Discord. We have amazing mentors and staff that will be helping answer those. So thank you guys all, and have a great rest of your day.
Thank you.